Hello everyone! In the previous lessons we showed that it was necessary to take into account the interactions between magnetic moments in a solid. In this lesson we shall see how such interactions naturally arise when the problem is treated quantum mechanically.
For simplicity's sake, assume that the local magnetic moment of every atom in the solid-state system results from a single valence electron occupying the energy level with the S-wave wave function phi of r, and thus having no orbital magnetic moment. In this case, the atomic magnetic moment is entirely due to the electron spin s, that is equal to 1/2, and the magnetic moment operator has the following form, so that its projection on z-axis can be equal plus or minus mu b. Now consider two atoms I and J with coordinates Ri and Rj, having magnetic moments mu I and mu j respectively. Our objective is to determine the interaction energy Uij of those moments as a function of their mutual orientation and the distance between them. In fact, we should express the operator Uij in terms of operators mu I and mu j. In these expressions, Si is equal to Sj, and both of them are equal to 1/2. The wave functions phi I and phi j of an electron in ith and jth atoms can be found from the corresponding Schrödinger equation. They are identical in form, but localized in different regions of space, having their maxima at r is equal to Ri and Rj respectively. Let us now consider the two-electron wave function for a pair of electrons in atoms I and J, where numbers 1 and 2 are the sets of spatial and spin coordinates of the first and second electron respectively. Since every electron has a half-integer spin, the electrons obey the Fermi-Dirac statistics, and the many-electron wave function changes sign upon permutation of any two electrons. In our case, we have the following relationship. In the absence of spin-orbit interaction, the wave function can be represented as a product of coordinate and spin wave functions. It is known that symmetric and antisymmetric functions chi of sigma 1 and sigma 2 correspond to the total spin of two electrons s is equal to 1 and to 0 respectively. Hence, the function phi of r1 and r2 is antisymmetric if s is equal to 1 and symmetric if s is equal to 0. That is, the symmetry of the coordinate wave function depends on the spin state. Since, from the viewpoint of classical physics, the values of s is equal to 1 and s is equal to 0 correspond, respectively, to parallel and antiparallel spins of two electrons, the symmetry of phi may be thought of as being dependent on mutual spin orientation. Let us construct the function phi of r1 and r2 from one-electron wave functions phi I and phi j. Taking into account that at I is not equal to j, these functions overlap weakly. So, for the function phi, we obtain the following expression, where eta is equal to 1 at s is equal to 0, and eta is equal to -1 at s is equal to 1. In order to express eta in terms of operators Si and Sj of electron spin at atoms I and J, note that their product is equal to 1/4 and -3/4 at s is equal to 1 and 0 respectively. Hence, for eta we have the following expression, so that the function phi of r1 and r2 depends explicitly on operators Si and Sj. It turns out that the existence of such relationship between the coordinate and spin wave functions leads to the exchange interaction between two electrons localized on different atoms I and J. Why is it called the exchange interaction? The requirement of antisymmetry of the total wave function imposes certain restrictions on the behavior of the coordinate and spin wave functions at the interchange of the particles, or in other words, when they change places. Since electrons at atoms I and J repulse each other, from Coulomb's law we have for the interaction energy the following expression. And finally, we can write it in the following way, where Aij is the energy of Coulomb repulsion, and Jij is the so-called exchange energy, or exchange integral, or the energy of exchange interaction. The latter is of purely quantum mechanical origin, and arises because of change of sign in the electron wave function upon permutation, in other words, exchange of two electrons. Since both functions phi I and phi j are exponentially localized at a distance about 1 angstrom from the corresponding atoms, it can be shown that Aij and Jij can be expressed in the following way. It is important that Jij falls off exponentially with the distance between the atoms I and J being maximum when these atoms are nearest neighbors. This is why the so-called nearest neighbor approximation is of frequent use. For different materials, the value of J varies widely, being typically in the range from 0.001 to 0.1 electron volts. Let us explicitly express the operator Uij of the pairwise interaction energy in terms of operators mu I and mu j of magnetic moments at atoms I and J. Taking into account the relationship between products of S operators and mu operators, we have the following expression for U operator. The sign of the second term in this equation depends on mutual orientation of the magnetic moments, since the product of operators mu I and mu j is greater than 0 in the case that the spin S of two electrons at atoms I and J equals to 1. Parallel magnetic moments, and the product of operators mu I and mu j is less than 0 if S is equal to 0, anti-parallel magnetic moments. It follows from previous equation that for the magnetic moments of ith and jth atoms, it is energetically favorable to be oriented in one direction if Jij is greater than 0, and in opposite directions if Jij is less than 0. In the case that Jij is greater than 0 for any pair of atoms in the sample, the total energy of the system is minimum when all magnetic moments are unidirectional. This is the ferromagnetic ordering. Next, as long as Jij is less than 0 for any two nearest atoms and negligibly small otherwise, the total energy is minimum when any two nearest moments are oppositely directed. Such a type of ordering is referred to as antiferromagnetic. It is reminiscent of a checkerboard order. In the general case, the sign of Jij may vary with the distance between the atoms I and J, resulting in rather complex magnetic textures, neither ferromagnetic nor antiferromagnetic. It should be pointed out that the very possibility of one or another type of magnetic order to take place in a given solid strongly depends on its crystal structure. For example, the antiferromagnetic ordering cannot occur on a triangular lattice because of frustration. Besides, in anisotropic crystals, different types of magnetic order may exist along different crystal axes. In this lesson, we understood the quantum mechanical origin of interactions between the magnetic moments in solid. We saw that the relationship between coordinate and spin wave functions resulted to exchange interaction between two electrons localized on different atoms. The exchange interaction is called so because the requirement of antisymmetry of their total wave function imposes certain symmetrical restrictions on the behavior of the coordinate and spin wave functions when the particles change places. Interaction energy of two electrons includes the Coulomb path and the so-called exchange energy, which has the purely quantum mechanical origin. The exchange energy falls off exponentially with the distance between the atoms, being maximum when these atoms are nearest neighbors. Thus, the nearest neighbor approximation is of frequent use. The sign of exchange energy determines the type of magnetic ordering in solid. For example, when the exchange energy is greater than zero for any pair of atoms in the sample, the total energy of the system is minimum, when all magnetic moments are unidirectional, and this is the ferromagnetic ordering.